Okay, as promised, we're just going to go over problem 2-4 from the slides. I guess this is something taken from the book. I might do a little bit more with it. I'm not really worried about it. Just follow the slide. And this is a good summary of a lot of concepts we've been talking about. And I think problems like this are really helpful. And if you did this already, or if you want to do this before we go over anything, you want to see if you really know what you're doing, I came up with an answer that the heat of the reaction, Rxn, is positive 295 kilojoules per mole. Now that's using the bond energies. So the way you do bond energies, this is just a generic equation. If you want to know the heat of a reaction using bond energies, that's not right. And this is part of the review, but I'm just making sure you understand it. Remember, using the heats of formation, it was the heats of formation of the products minus the heats of formation of the reactants, and that gives you the heat of the reaction. Using bond energies, it's kind of the opposite. You add up the bond energies of all the bonds that are broken, which really those are the reactants. So it's almost the opposite equation, minus the sum of the bond energies that are formed. So to do these problems, you need a chemical equation, you need to balance that chemical equation, and you need to know the electron dot structures showing the bonds, so that you can count the total number of each type of bond. So I'd like to go through that with you. And let's see. Okay, I guess we should do all of these. So the case study of Freon-12. So the electron dot structure. I think that's it. It's just carbon in the middle, because these are symmetric, and then 2 fluorines and 2 chlorines. You can do all your rules for electrons. And if you did this slightly differently, like you put the chlorines and the fluorines in different positions, that does not matter. All of those positions are equivalent. So if you turn the molecule, it wouldn't matter. We don't spend a lot of time talking about 3-dimensional structure, but if you want to, carbon is in the middle, and the 3-dimensional structure is called a tetrahedral. I'm not going to do the dots. So it's not a flat square, it's a tetrahedral with bond angles of about 109.5. So all the positions in a tetrahedral are equivalent. So this doesn't matter, and that is irrelevant for this calculation, because all we need to know is that there's 2 bonds between carbon and chlorine and 2 bonds between carbon and fluorine. That's it. Formal chemical name. You might find different things for this one. What do I have here? This is the SDS sheet that I found online. I'm not gonna, you can look this up yourself. And yeah, okay. Those of you that have had organic chemistry know that anything with 1 carbon has the prefix meth. So like CH4 is methane. So this is actually I think you put chloro first, right? Alphabetical. It's been a while since I've done organic nomenclature. Dichloro, difluoro. I make a joke about the spelling of fluoro in the homework, but this is a joke. Dichloro, difluoro, methane. But the trade name is Freon-12. Google or look at an SDS sheet for relevant chemical and physical properties. Okay, you can do that. You don't need me to do that. I think students, when they did this in class, they just looked it up on their phones. There's a lot of them here. Okay, I'll let you do that. You can just go list what you think are some of the other interesting properties. Especially, remember, this was used as a refrigerant in large tanks carried around and pumped into pipes and things like this. So what would happen if you were exposed to this? But you can do that one. So C, do that on your own. D, write the appropriate chemical equation for the abstraction, again that's a good word, of a fluorine atom by a hydroxyl radical. Okay, so we're taking a hydroxyl radical, which we can show like that, and we'll do a more explicit diagram. And CF2Cl2. Okay. And let's be careful here. I didn't put this in my notes. These are all happening in the troposphere, or excuse me, well, they could be happening in the troposphere and the stratosphere, but they're happening in the atmosphere. So we want to show the abstraction. So of a fluorine, we could abstract a fluorine, or a chlorine, but we're doing a fluorine. So that's fine. So that's going to be so this is just pulling off a fluorine. You can write that different ways. I just put it HOF, I'm not sure why, rather than FOH. You can do FOH. Doesn't really matter, does it? And then what's left behind? Well, that seems pretty easy, just one less fluorine. Okay, so that's what's going on. That's not too tough. And what's letter C? What's the next one say? Okay, do the electron dot structures and then calculate the heat. Fine. Well, we already have this one, so I'll rewrite it. So it's carbon connected to fluorine, and I'm just going to do it differently to show that it doesn't matter. For this problem. Oh, it balances, right? It's not we don't need to, everything's 1 to 1, so I don't think that's really a problem. And you might recall a hydroxyl radical looks like that. Okay, so what are we doing over here? We're taking a fluorine and we're forming a new bond. I don't think that's a radical anymore. So we're forming a new chemical bond here between one of these fluorines. And then what we're left behind with is a radical on the carbon. Yeah. So we're breaking that bond, so we've got, let's just make sure we're doing this right. So we've got that. I guess I could put a plus sign there. And then that fluorine is gone, so we've just got this chlorine, and that fluorine. Let's check it, because I want to make sure I don't make any mistakes on this one. Yeah, this one shouldn't be too tough. Okay, so the way I like to do these is to calculate the heat of the reaction is bonds broken. So I put those in brackets. So these are all the bonds that are broken, minus the bonds that are formed. So what we have to do is we have to look up the bond energies, but I want to show you something here. This is pretty simple. We're breaking one bond and forming another bond. We're not breaking everything apart, but I'm going to show it that way. But then the math is going to be greatly simplified by the fact that we're breaking that bond and we're making that bond. That's it. Not all chemical reactions are that simple, but if you want to do this, the full way, oops. So let's see, how many bonds are we breaking? We've got So we're going to take the bond energy of a carbon-chlorine bond, so carbon connected to chlorine, and multiply that by 2. Well, that's 2 carbon plus 2 times the bond energy of a carbon fluorine bond. So we're pretending, if you will, when we do this math, we're pretending that we're breaking everything, but we're not. So 2 of those, plus 1 oxygen connected to hydrogen. I think that's right, yep. And then what are we doing over here? The bonds that we're forming, but not really. So we have, what do we have here? We have 2 carbon connected to chlorine, and 1 carbon connected to fluorine. It's really kind of not very efficient to do it this way. Just go to the bonds that are broken and formed, which we're going to see anyway. So we've got 1 of those, and then over here we've got an oxygen-fluorine bond, and we still have the oxygen-hydrogen bond. Do I get them all? So we're breaking all these bonds and making all these bonds only for the math, only for the thermodynamics. That's called a state function. It only matters where you end up and where you start, not how you get there. So 2 of those, 2 of those, 1 of those, 2 of those, 1 of those now, there and there. Now the thing is, some of this stuff cancels. We don't need to look that bond up because it's the same as this one. We don't even need to look it up. The carbon-chlorine bonds aren't broken and they aren't formed. So we can get rid of those. And we can even get rid of, there's 2 carbon-fluorine bonds here, there's 1 carbon-fluorine bond here, so why don't we just get rid of that and make that 1 of those bonds. Boy, doesn't that become easy. Because all we're doing is breaking a carbon-fluorine bond and making an oxygen-fluorine bond. That's all we're doing. We could have just jumped to that. But for the sake of argument, for the sake of applying this equation, and I didn't write this over here, it's reactants minus products. Now let's look up the numbers. And make sure I did this right. So carbon-fluorine bond is pretty high actually. 485 kilojoules per mole minus 190 kilojoules per mole. I think that's right. And if I did my math right, the answer I told you at the beginning of this lesson is positive 295 kilojoules per mole. And on the slides, it says, great, what does all this mean? There's a few things that we take away from this, some of which are going to carry over to the next chapter. And if you want to think about this for a second before you just hear me give answers. So I'm just reading this one. As we will learn in the next chapter, hydroxyl radicals are common in the troposphere. In other words, down towards our level. These are very, very common. And what they end up doing is they end up reacting and acting as you see here, what's called a tropospheric sink. They essentially have the effect of scrubbing the troposphere of pollutants before they get to the stratosphere sometimes. So that's kind of interesting, is it's a chemical defense mechanism that nature has in the troposphere to keep things from getting up into the stratosphere and damaging. That is really fascinating stuff. That's the concept of tropospheric sink. So the question then becomes, cool, based on all this work we just did, how likely is it that hydroxyl radicals will actually do that with Freon-12? So Freon, let's say it escapes from some factory. It goes up, it's a gas under normal conditions. It goes into the troposphere. It's heading towards the stratosphere where it can participate in ozone depletion by forming chlorine and fluorine radicals, mechanism 2, yada yada, okay? What do you think? Would it work very well? Would hydroxyl radicals prevent this molecule from getting through the troposphere? Well, the answer, as you might imagine, since CFCs are an ozone depleting chemical, the answer conceptually is no, because doesn't that stuff get up there and cause damage to the ozone? Yes, it does. Why? Well, this is why. This is endothermic. This process requires a lot of energy. So if it requires a lot of energy, it might not happen very easily. So as this goes, it would take certain conditions, I'm not even sure what it would be, high temperature, high pressure, to make the reaction go. So this is probably unlikely to be very effective at removing Freon-12 by the tropospheric sink of hydroxyl ions. That's a pretty scientific way of explaining it, and it all comes down to some of the data that we've talked about here. Okay, and ladies and gentlemen, that is chapter 2. That was an overview of these lessons, so make sure that when you do the homework, you go back to the book and you look at things in more detail to answer the questions. Ultimately, what does it come down to? If you can do the homework problems, you're fine. That's all I'm asking for. We're not asking you to understand every last letter of every single chapter. We would never get that far in this course. So we're being very selective with this chapter and subsequent ones. So take care, and we'll see you for chapter 3.